I switched this on and I'm audible, I guess, right? Okay, great. Well, thank you for the kind introduction and thank you for the invitation. I'm quite excited to talk to you about rates and populations of compact binary coalescences. As the subtitle suggests, this is going to be a very gentle introduction to this topic. If one wants to go really in depth, I think an entire semester is actually required. But nevertheless, what I hope is that by the time I'm done with the two lectures, today and tomorrow, I would have enthused you sufficiently so that you look at some research papers or at the very least come and talk to me later on and talk more about this kind of research, which I hope you will find quite interesting and exciting. All right, so what I'm going to do here is I'm going to jump back and forth between the slides and the blackboard. So what I'm going to do first is just write down like a table of contents to give you an idea of what exactly I'm hoping to cover over the next, well, definitely this session, and I will also briefly tell you what I'll cover in the next session. All right, so to start off with, I want to put down what I'm calling a context. What I mean by the context over here is essentially what has the LIGO, Virgo, Kagra network of gravitational wave detectors seen so far. So what I've abbreviated this as LVK. This basically stands for LIGO, Virgo, and Kagra, which is your detector network so far. Is everything okay? Yes. This? Okay, all good. Okay. I also need to be mindful of this. This is precariously oriented, so I'm just going to write down the table of contents here, and then I'm going to go over the other side where everything looks safe. Okay. So what has LVK detected so far? Okay. So that's the first question that I want to try to answer, and that will be basically over here on the slides. Hopefully, the slides are sufficiently catchy and attractive to get your attention. The next, what I'm going to do is I'm going to talk about two important preliminaries before I can even talk about rates and populations, and that is how do we detect GWs, gravitational waves. So how do we detect them in the first place? And the next, given that you have seen a gravitational wave, that is, you have a stretch of data where you know there is a gravitational wave event, given that, what can you say about the source that produced them? I guess this is GW, so it should be them. Okay. So those are the two important things that I'll need to cover. Again, it's going to be in brief, but I'm going to put down some important equations and also share with you some of the jargon that is used in data analysis, gravitational wave data analysis. Now, once we have these two things covered, then I will give a first introduction to how do we calculate the rate of events. Now, what do I mean by the rate of events? So this has a very specific meaning. The rate of events basically means number per unit co-moving volume per unit source frame time. Okay. Why I am specifically saying source frame time will become clear once I actually go over the derivation. Okay. So that's what I mean by rate. How often do they happen intrinsically out there in nature? And finally, for today, I'm going to also cover briefly if supposing you had a collection of gravitational wave events whose parameters you know. So suppose you have done this. So you know what are the parameters of the source. For example, you know the masses of the binary black hole that produce the gravitational waves. Then if you had those, what is the distribution for this two set of lectures? I will just focus on mass distribution, but in general you can also do that for other parameters like spin, etc. But what is the distribution of source parameters? Okay. All right. So this is what I plan to cover today. What I'm going to do tomorrow is go more in depth on this particular aspect of rate. Today it will be very preliminary and very straightforward, but tomorrow I will point out what are the caveats to the preliminary method and then go more in depth with a more detailed derivation. Okay? Alright, so this is what I plan to do. So let me then start off with the context. Alright? Should I switch off the light? Or maybe you just watch TV here, right? I mean, is that fine? Okay. Okay. Sorry to make you go back and forth like this. It's fine. Okay. So I don't know the switch. So okay. Good. Okay. All right. If I do this, what happens? I think I accidentally moved the title also, but never mind. It's fine. All right. So moving on. Context as promised. All right. So I suspect, even though you may not be in the field of gravitational wave data analysis, you definitely would have heard about the first detection of gravitational waves, which happened in 2015 on September 14th. This was the detection of a binary black hole merger. So there are certain interesting things about this binary black hole merger. The first is that the masses were approximately 30 solar masses, and this came as a big surprise because from X-ray observations, we did not expect to actually see such very large, massive black holes. So this came as a big surprise that these kinds of black holes actually exist in nature. That was one. The source distance, that is, it happened at approximately 410 megaparsecs, that's about 1.2 billion light years away. A parsec is about 3 light years. It was detected by these two gravitational wave detectors. Essentially, they are Michelson interferometric detectors with 4-kilometer long arms. This particular detection happened or was detected by the two LIGO detectors, one in Hanford and one in Livingston. Since then, another detector has come online to join the network, and that detector is known as the Virgo detector. That is in Italy. These two, if you didn't know, Hanford and Livingston, that's in the United States. Now, once you had this 3-detector network, the first binary black hole was detected in the first observing run. Then perhaps the next most famous event was GWS 170817, which was the merger of a binary neutron star. This arguably, of course, there is still some, I guess people are not fully on consensus about this, but a lot of people believe this is the astrophysical discovery of this century. The merger of a binary neutron star that was not only observed by the gravitational wave detectors in gravitational waves, it was also followed up extensively by electromagnetic telescopes worldwide. And what is a fact, this is not an opinion, this is a fact, this particular transient event was and still is the single most followed up event ever in recorded human history. Okay, so it was a particularly exciting and particularly rich scientifically event. Now, why do I say that it was a particularly rich scientific event? Well, first of all, because of the fact that you had your three gravitational wave detectors, we were able to triangulate the source within some error bar in the sky. This is this green patch that you see over there. We were able to triangulate it in the sky. This allowed telescopes, electromagnetic telescopes, to slew to the location in the sky where the event happened. And from the electromagnetic counterpart, we were able to do all kinds of very interesting science, which I'm not going to go over. We were able to study matter at extreme densities. We now know that some of the heavier elements of the periodic table are synthesized in the merger of neutron stars. We now know that at least one source of short GRBs are mergers of binary neutron stars. And we now also know that at least one source of kilonovae are binary neutron star mergers. In case you don't know what a kilonova is, it is an explosive transient event which is about 1,000 times weaker than a supernova. Its provenance was unknown or not confirmed, at least. There were speculations. And now it is confirmed that at least one source of kilonovae are the merger of binary neutron stars. Okay. So this was me trying to be a little fancy and trying to catch people's attention. In a less formal talk, I would have said that, if supposing you have proposed to the person you love, the gold in that ring probably was synthesized in the merger of neutron stars. But given that this is a more formal lecture, I avoided all of that. Okay? Sorry? Oh, you think it is appropriate? All right, I like it. Romantic man. That's the way to go. All right. Moving forward. Now, other major hits of the LIGO Virgo detections that we have seen, this happened in the third observing run. So there were two neutron star black hole events, and don't let this simulation mislead you. Even though it is speculated that there should have been an electromagnetic counterpart, no electromagnetic counterpart was observed. Nevertheless, we are pretty confident that these two events are indeed neutron star black hole mergers. Now, note that not all neutron star black hole mergers are expected to produce electromagnetic counterparts, and the reason is this. In order for an electromagnetic counterpart to be produced, you need the neutron star to disrupt. In order for the neutron star to disrupt, you need the tidal field to be strong enough. Now, in order for the tidal field to be strong enough, you need the neutron star to have disrupted sufficiently close to the black hole. Okay? Now, if the black hole is extremely large in comparison to the neutron star will basically get swallowed up whole. The tidal field is just not strong enough. However, when the mass of the black hole becomes comparable to the mass of the neutron star, say a factor of a few, then the tidal field before the neutron star has entered the ISCO, the innermost stable circular orbit of the black hole, is sufficiently strong and it disrupts outside the ISCO, and then you will have an electromagnetic counterpart. Okay? So one of those events at least was based on this argument supposed to produce an EM counterpart. Maybe it did produce, it was just too dim to be observed. We do not know for sure. All right. Now, another very interesting event from a population perspective, which also happened in the third observing run, is this event called GW 190814. Why is this particularly interesting? This is an event which contains at least one black hole, which we are sure, and it contains another object which is either the heaviest neutron star ever detected or it is the lightest black hole ever detected. We do not know what it is. It is one or the other. Okay? So this is another very interesting event. I have put down the source parameters that were inferred. So you have the larger object at 23.2 solar masses, definitely a black hole. And you had this other object which is at about 2.6 solar masses. If it is a neutron star, it's the heaviest ever. If it is a black hole, it's the lightest ever. Okay, so very interesting object. Okay. All right, and then finally, I just wanted to point out another very interesting event, which is GW 190521. This is the heaviest binary black hole merger detected to date. It has one mass at 85 solar masses, another at 66 solar masses, and a total of 142 solar masses after the merger. So that's the final mass. Okay. All right. So any questions so far? I guess all of this is fairly straightforward. Okay. So this plot is a plot that pretty much all gravitational wave astronomers like to show in their talk. This is known as the stellar graveyard plot. Okay. So what does this plot actually show? On the y-axis, you have masses. On the x-axis, you have basically nothing. It's just to spread out the graph. What you have over here in blue are your black holes. And after the black holes merge, they produce a third black hole. That's what blue plus blue to blue represents. Okay. Now, you also have orange plus orange going to something that corresponds to neutron star mergers producing either a neutron star or a black hole. We do not know yet what the final object is after the merger. And I think you will also find, yeah, like this one, a neutron star merging with a black hole to produce a black hole. Okay. And depending on where they lie on this plot, it tells you how massive they are. Okay. Now notice that these things in red that you see over here are basically black holes that have been inferred from electromagnetic observations, indirect measurements from X-rays. Notice that they all lie below these blue fellows. So that's what I said initially. It came very much as an unexpected surprise that we are seeing such massive black holes, because they clearly are quite distinct from the kind of black holes that are inferred through X-ray observations. Okay? All right. Okay, so now, not yet. Yes. Neutron stars, pulsars. Yeah. Which event? The one with the EM counterpart, I believe, will be this one here. Yeah. This plus this produce that. Okay? Nothing. It's just meant to give you a pigeon-like feeling. So it spreads out, right? So it's an artistic thing, that's all. Yes? Yes. Yes, source frame. Yeah, it's what is called source frame masses. I haven't yet gotten to that. Maybe I'll get to it. Yeah. Do you understand the difference between source frame and detector? I can explain it if you like. Yeah. And these blue ones are like kind of completely different. Exactly. Yeah. So, is it some? Maybe this is a later question that maybe I'll ask it. Okay. Sure. Yeah. All right. Any other questions? If not, I will now move to the blackboard portion of my talk. All right. So, next in your table of contents is detection preliminaries. All right. So, I've talked about a bunch of detections. If you're not familiar with it, the first question that may have arisen is, how do we detect these gravitational waves in the first place? All right. So, now, as you know, gravitational waves essentially manifest themselves as strains, change in length divided by length. And what these gravitational wave detectors measure are differential strain arms. And the differential strain is essentially measured as a difference in the change in length. What I mean by that is, if you have a strain and you multiply that by a length, what you will essentially get is another length, right? So delta L over L is your gravitational wave strain. So this is what shows up at the detectors. What you measure is delta L, which is L into h. It turns out that this is of the order of 10 to the minus 21 to 10 to the minus 23, extremely tiny. What that means is for a 4-kilometer long arm, this corresponds to a change in length that is smaller than the radius of the nucleus of an atom. So it is an engineering marvel that we are even detecting these things in the first place. Okay. Now, as you can imagine, because these changes in length are so small, in spite of the best efforts from the best engineers, you still cannot completely get rid of noise. Okay. So eventually what you end up seeing is a strain as a function of time which is oscillating, which is a sum of the noise in the detector as a function of time plus your gravitational wave signal. Okay, so this is what your detector actually sees. The task then is to extract this gravitational wave signal from. So how do we do this? Now, in order to meaningfully extract the gravitational wave signal from the data, you need to have a good understanding of your properties of noise. And once you have a good understanding and a way to characterize noise, you should be able to extract that signal from the data. All right, so let's talk a little bit about noise. All right. What we assume, and this is a fairly decent approximation, there are exceptions, but to a very good approximation for a lot of the time, the noise n of t can be modeled as a zero mean Gaussian random variable. Okay. Now, if you can model your noise as a zero mean Gaussian random variable, what that means is that your noise n of t is completely characterized by a quantity called the power spectral density. Okay, and this is typically just written as PSD for short. Okay, so your noise is completely characterized by this power spectral density. You can think of the power spectral density as a measure of the variance of this Gaussian. So the Gaussian is defined as in terms of a mean and a variance, right? So this power spectral density can be thought of as a measure of the variance of that noise. Okay, fine. So all right, so what is this power spectral density? So suppose that I have Px, okay, which is a probability density for so suppose that Px is a probability density for the value of x, where x is some random variable associated with a random process, okay, at some time t. Okay. The expectation value of x at that time t is an ensemble average. What I mean by an ensemble average is that supposing you had very many detectors that are all affected by the same type of noise, okay, and say you looked at the value of X or S or whatever your data is at that time t for all those detectors, and then you histogram the X, okay. Then from your definition of expectation, you have X is equal to integral, okay, and with appropriate limits, say from 0 to infinity, all right. Now this is how you would, for example, determine what is the expectation value of the noise, right? But unfortunately it turns out that having very many detectors is deeply problematic because one detector costs about some 700 to 800 million dollars. So having very many detectors is a big problem. So can we, instead of doing an ensemble average, can we do something else? So this is where we invoke something called, and I'm sure you have come across this before, is called the ergo principle, okay? So what do we do? All right, so ergodic principle, we invoke it. So the basic idea here is that if the statistical properties of X, say X is Gaussian distributed. So if supposing the statistical properties of X here would mean the mu, meaning the mean, and the standard deviation of variance. So if the statistical properties of X don't change with time, so then I can convert my ensemble average to a time average, provided I take a sufficiently long stretch of data, okay? So your same ensemble average is equal to limit t tends towards infinity 1 over t all right. So essentially you have converted your ensemble average to a time average, and basically your donors and the government are all very happy because they don't have to build very many detectors. They just have to build one, and for one also it took a long time for the paisa to get approved. So good thing we are able to do this, okay? All right. So now we are trying to get to power spectral density, right? So we are going to use the definition of this expectation value to determine what is the power spectral density. So first, let me write down a function called the autocorrelation, okay? So the autocorrelation is essentially a two-point correlation. This okay, ensemble averaged, which can be also time averaged using ergodic principle, right? So this is your autocorrelation function. It's a function of tau and not a function of t, okay? Is this clear? Any questions on this? All right, so now the power spectral density, PSD, is just related to or proportional to the Fourier transform of this autocorrelation, okay? All right, and mathematically I will just write it down. So I'm not going to go over the derivation of this, but after you employ the Fourier transform, what you end up getting is the following. The PSD as a function of frequency is equal to twice and this, it turns out, is equal to okay, Fourier transform of your autocorrelation function, if you work through the derivation, turns out to be this. Okay. Any questions? Now there is a slight technical subtlety which I just want to point out. Typically what is used in your detection process to extract the signal from the data is not just the power spectral density, but a specific kind of power spectral density called the one-sided PSD. The basic idea of this one-sided PSD is just to make interpretation more straightforward. The idea is that if your data is real and then you determine what is the PSD, then this PSD turns out to be an even function. Whatever you have along the positive x-axis as your PSD is reflected, it's symmetric along your negative frequencies as well. So what you can then say is that I can redefine my PSD such that it's only defined in the positive frequency, and then I will double the power. So I will multiply by a factor of 2. So instead of having to do any integration from a negative frequency to a positive frequency, you can just do the same integration from 0 to the positive frequency, but now you have pushed your power up by a factor of 2, right? Because the function is even. Does that make sense? So typically what is done is to use this thing called a one-sided PSD for that reason. Okay? Right. Okay. So now that I have defined the PSD, I want to define what is an optimal detection statistic. So suppose as we've always been supposing so far, that your noise is a stationary Gaussian random variable whose variance is defined by the PSD, one can show that the optimal detection statistic is what is known as the signal to noise ratio, rho, which is given to you by this operation. So what is this operation? If I have two time series A and B and I take their inner product, I'm going to define my inner product as 4 times the real part of So this is by what I'm defining as my noise weighted inner product between two time series A and B. You have to first take the Fourier transform And then you have to perform this operation. And then you get the definition of this noise-weighted Euler product, where Sn of f is, as usual, the one-sided PSD for noise. Okay? Yeah. Yes. Yes. Correct. Per detector. And then when you want to come up with a network SNR, you add them in quadrature. So it's the square root of rho square for detector 1 plus rho square for detector 2. Okay. I'm not going to go into that, but since you asked, I mentioned it. Okay. All right. So next point is, what do I mean by hat? Hat is basically normalization. So what I mean by hat here is, okay, so this is how I'm defining as normalizing this H. Okay. Now I have been a bit vague here. What exactly is this H? So you have a signal that is sitting in the data that you are trying to extract, and then you are performing a projection of the strain onto this normalized H. So the H here is what we call a template. So essentially, you can think of a template as our best guess of what the signal is in the data. But of course, I mean, we are not God, right? We don't know what the signal is in the data. So how do we know what template to use in the first place? Because the better the template is of a representation of the signal, the larger the signal to noise ratio will be, meaning the better your ability to extract the signal from the data will be. But you don't know what the signal in the data is, so it's a sort of catch-22 situation, right? So in order to circumvent this, what is essentially done is to use brute force, where we use an entire bank of templates consisting of literally millions of templates, and every template is filtered using this operation, and the signal to noise ratio is calculated, and the template that produces the largest signal to noise ratio is said to be the template that is best representative of the signal in the data. Okay? Does that make sense? Any questions? Yes. Okay, so what you can further show is that because rho is particular operation where S involves a random variable in its sum, right? It is noise plus signal. So rho also is a random variable. Okay. What you can show is that on average, if your template is a perfect representation of the signal in the data, then rho on average will equal what is called the optimal SNR, rho opt, which is the square root of 4 times the real part of okay. This is something that you can show. So on average, you will get this to be your signal to noise ratio. All right. Okay. So one second, I might have made a typo. I think that it should be you mean here, right? I think it's minus t by 2 to t by 2. I made a typo. It's a mistake here. So thanks for catching that. There's a typo. Minus. Okay. Sorry. Ha. Yes, and it will be 4 times the real part of that. Okay. Anything else that is confusing? If you see a typo, please let me know. Okay, if this is clear, then let me go back to this board. Okay, so the next question is, how do you construct your templates in the first place? Okay, so how do you get H? Now the way you get H is basically by, in some way or the other, numerically solving in two-body problem. Okay, now there is no analytical solution in GR for the two-body problem. So what is typically done is to break up the production of gravitational waves into multiple phases. Okay, so when you have two compact objects that are going about their mutual center of mass, you have radiation of energy, that is gravitational waves carry away orbital energy and angular momentum that causes the black holes in the binary to inspiral. Now as they inspiral, they will get closer and closer to each other until they eventually merge. Now when the inspiral is sufficiently slow, then one can use a particular kind of formalism known as Newtonian formalism. Then when you come to the merger, it turns out that there is no approximation that you can use that can accurately model the waveform, and you have to use full-blown numerical relativity. Then after black holes merge, they basically ring. You've already heard this term before, and there you have to use black hole perturbation theory. Okay, so stitching all of these things together, one can construct different kinds of waveforms. There are different families of waveforms. For example, the inspiral merger ring down IMR norm waveforms are there. There is the effective one-body waveforms. There's a whole host of them. Okay, but since this talk is specifically focused towards data analysis, I'm not going to talk to you about the details of how these waveforms are produced, but I'm just going to leave you with what are the parameters that determine the shape of the waveform. Okay, so your waveform template or your gravitational wave signal depends on a bunch of source parameters. Theta is a union of intrinsic parameters as well as extrinsic parameters. Okay, intrinsic parameters are parameters that are intrinsic to the source and are not therefore observer dependent. These intrinsic parameters are the two masses m1 and m2, the two spin vectors of the individual black holes. So each of these are basically three components: S1x, S1y, S1z, S2x, S2z. Okay, so those are your intrinsic parameters. Now, your extrinsic parameters is also a union of two sets of parameters which I am calling theta f and theta h. Okay, so why am I calling it this way? Okay, I have a lot of things. So the gravitational wave signal, if supposing we believe GR, which we do, then your gravitational wave signal has essentially two polarizations, an H plus and an H cross. Okay, the way to think about this, if you are not familiar with it, is if supposing you had a circular garland of masses, and if you had a plus gravitational wave that is in this circular garland perpendicular to the plane, it will stretch and squeeze that garland into perpendicular ellipses, okay, back and forth. Now, supposing you had a cross polarization, purely cross polarization gravitational wave that is incident on this circular garland, then the two axes that were perpendicular rotated by 45 degrees, okay? And then again you'll have this back and forth motion, all right? So what you end up seeing in your gravitational wave detector is a linear combination of the two polarizations, and this linear combination is F plus H plus plus F cross H cross, okay? Now, this F plus and F cross are known as the antenna pattern functions, okay? So, they can be thought of as the response of the detector to the individual polarizations, okay? Now, these antenna pattern functions are dependent on what I have called theta f, okay? And your H plus and H cross, the two polarizations, are functions of the intrinsic parameters as well as what I have called theta h, okay? All right, so theta f is a function of three parameters: your right ascension, declination, and polarization angle. Right ascension and declination basically give you the location of the source in the sky with respect to the detector, right? So depending on the orientation of the detector with respect to where it is located in the sky, obviously will determine your amplitude detector. And theta h depends on the luminosity distance. So this is an extrinsic parameters that enters the H through H plus and H cross. Further away your source, the weaker the gravitational wave signal will be, not surprisingly. It depends on the inclination of the source with respect to the line of sight, okay? So that's given to you by iota. So this is inclination, this is luminosity distance, and because you have an oscillatory kind of motion, it will also depend on the time at coalescence as well as phase at coalescence, okay? So there are a whole bunch of parameters on which your gravitational wave signal as measured by the detector depends on, okay? Any questions on this? Yes, alpha and delta are the right ascension and declination. These are locations on the celestial sphere. So where in the sky? So your H must depend on that because your gravitational wave detector is not isotropically sensitive, okay? So your gravitational wave detector is most sensitive at the zenith and it's least sensitive in the plane of the detector, okay? So what that means is your antenna pattern function must reflect that. So it should depend on the relative orientation of the detector with respect to where the source lies. So that's why your alpha delta comes in, and it depends on the polarization angle as well of the gravitational wave, okay? Any other questions? This is the time at coalescence and phase at coalescence. Think of simple harmonic motion, right? You need some, A sine omega t plus phi, right? So at a certain t, you need to know what is phi. It depends what your time at coalescence was and what your phase at coalescence was. So that's, you can make an analogy with simple harmonic motion if you like, okay? Correct, yes. So alpha delta is the location of the source independent of the detectors. But your anti-pattern function has to account for the fact that how your detector is oriented with respect to the location. Okay. Okay. These are all your parameters that determine the gravitational signal. So here I just want to show you a little animation that was done by Alex Nids. It's a very nice animation of how we actually extract the signal from the data. So what you notice over here, oh, I should probably have the pointer. Okay. So what you notice over here at the bottom in black is your gravitational wave, is your detector strain, okay? And then you have a template. Now, of course, the strain is a time series. So you don't know at what time your gravitational wave event has happened. So what you essentially need to do is you need to take your template and time slide it across your detector time series. And when the gravitational wave template perfectly aligns with the signal in the data, you will see a peak in your signal to noise ratio. And that's how you know, okay, look, there's a gravitational wave signal in the data. Okay. So this is essentially how match filtering works. All right. And this output that you see over here is essentially, okay, I've erased the formula, is the projection of the detector strain onto the normalized templates. That's basically what you're seeing as the output here. Okay. It has to perfectly align with the signal in the data at the correct time. So if supposing the gravitational wave signal, say you have a 2-day long data stretch, and supposing the gravitational wave signal happened yesterday, but you are moving your template on the data that happened today, you will see nothing. So you need to make sure that you slide your gravitational wave template to the data that was taken yesterday at the correct time, such that when there is perfect alignment in time, you will have this peak in your signal to noise ratio, right? Yes. You cannot see the signal inside the black thing. But when you do the operation, the signal to noise ratio operation can see things. Okay. And that is getting plotted here. So is the signal to noise ratio this optimal statistic that pushes it above the noise, if you like. Okay. Yes, those are some technical data I'm not getting into. This is very, I eventually want to get to rates and population, but yes, there's band passing and all that is also there. If people are interested, I can talk about that, when we over coffee or lunch or something. Okay. Any other questions? Yes. Correct. Yes. Mm. Yes. Yes. Okay. Right. Right. Yes. That actually gets me to my next point. Thank you for asking. All right. So I will come to my next point. And this is what is known as the notion of a background distribution. Okay. All right. So I think basically your question is, at what point can I say that I've actually seen a gravitational wave event? Or in other words, how high your peak of this SNR time series should be so that I can say, yes, I've seen a gravitational wave event. Should it be this high, that high, that high, how high? Okay. So one has to quantify this properly, all right? And the way we quantify it is by having a good understanding of what is known as a background distribution. All right. So, supposing I have a stretch of data, I have lots of data where I know that there is no gravitational wave signal, okay? It's only noise. So what I can do is I can perform this match filtering operation with multiple templates, etc. And I can construct a histogram which is essentially a conditional probability density on the signal to noise ratio given noise. Okay, so this is essentially known as your background distribution. In other words, you are asking yourself, what kind of signal to noise ratios does noise produce? Okay, so supposing I'm just drawing something. Supposing noise produces a distribution like this. Okay, at some value, let us say it peaks. Okay, so you can then define a particular quantity called false alarm probability. Okay, so how do you define this false alarm probability? Supposing you have a gravitational wave, or supposing you have an event, you do not know whether it's a gravitational wave event or it is just noise. Okay, so then suppose it shows up and you find that it has a signal to noise ratio which is, say, rho star. All right, so you have some event which produces a signal to noise ratio rho star. The false alarm probability is defined essentially as this area. Okay, it is the integral from rho star to infinity of okay, so this is your false alarm probability. So it is telling you how likely is it that you can have a noise event that produces an SNR at least as large as rho star or higher. Okay, so then what you can do is you can then define a criterion for your detection. What you can say is that if my false alarm probability is less than a certain value that I choose, then I will say that I have detected a gravitational wave signal. Okay. Now, for the very first detection, this false alarm probability threshold was extremely stringent. It was what is called a phi sigma or greater event. Okay. What do I mean by a phi sigma event? What I mean is that your rho should be so large that it lies 1, 2, 3, 4, 5 standard deviations away from the median of your distribution. If the distribution is Gaussian, it's mean also. Median and mean, same thing. Okay? Does that make sense? And this corresponds to, I believe, if you can check it maybe on Wikipedia or something, but I believe this a phi sigma event corresponds to a false alarm probability of 1 in a million. So 0.001, 6 zeros, 1. Okay. So it turned out that for the first event, the detection statistic was so large, it not only exceeded the phi sigma, the background, there was actually no background event that was even existing at those regimes. So they actually had to extrapolate the background distribution all the way to that ranking statistic to estimate what is the false alarm probability. So it was a screamingly loud event that we were sure was a gravitational wave event. Since then, the strictness of what is considered a detection has reduced. It is now defined in terms of a quantity called P astro. And I'm going to come to that tomorrow. I'm going to explain what I mean by P astro tomorrow. But at least for the first detection, it had to be a phi sigma event. So your ranking should be 5 standard deviations or larger than the mean or median value of your distribution. Okay. Any questions? Uh, yes, and then these background studies are constantly updated as the data keeps coming in. Yeah. Exactly. Yes, exactly. Yeah. Any other questions? You can think of it that way also. Yeah. But the notion of, I think, false alarm probability exists both in Bayesian and frequentist, I believe. Yeah. I believe that is correct, but you can check it. Yeah. Oh, of course, some of you who might have been looking at some of the LIGO papers may wonder, yeah, you're talking about false alarm probability, but over there they talk about false alarm rate. What is the difference between false alarm probability and false alarm rate? It turns out there's nothing very mysterious there. The false alarm rate is basically a rescaled version of the false alarm probability, where essentially you divide the background that you have is taken over a period of time. So that period of time you have to basically divide here, and then you will convert your false alarm probability to a false alarm rate. That's it. Okay. So this background was obviously taken over a stretch of data that stretched a particular span of time. Just divide FAP by that span of time and you will convert your false alarm probability to a false alarm rate. How often per day, per month, per year will this happen? Okay. Turns out that this event was so loud and it was so far away from the background that I believe you can, if I'm not mistaken, the false alarm rate was actually smaller than 1 per the age of the universe or something like that, some ridiculously small number. Okay, extremely small. All right. Okay. So I already talked. This I'm going to talk to you about tomorrow. How currently instead of false alarm probability for a detection, they use this thing called P Astro. I'll talk about it tomorrow. Um, okay. For now, let me continue on with. I will now move from detection to parameter estimation. Okay. So this is again related to the question that I'm sorry, I don't know your name, but the question that you asked. Yeah. So the question that you asked was, what kind of template should I use? Is the template sufficiently sophisticated to be able to extract the signal from the data? Right? So I can kind of repurpose this question and ask a couple of other questions. Okay. The first question I can ask is, fine, you have extracted the signal from the data, but can you guarantee me that the template that was used to extract the signal from the data is an accurate representation of the signal in the data? It turns out the answer is not always yes. It is not always an accurate representation. The technical terms that they are used for this is searches are effectual but not faithful. So the template method, the template bank method is good at pulling out the signal, but so that means it's effectual, but it is not very good at telling you what are the parameters of the source that produce the signal. Okay, so effectual but not faithful. So then you want to ask the question, but I want to know what are the parameters of the source, right? So in order to determine what are the parameters of the source, one uses a Bayesian framework. So very quickly, I'm going to write down what is Bayes' theorem. I suspect some of you already know this, but nevertheless, the conditional probability of the source parameters given your data can be written as follows. Okay. So this quantity is called the posterior density, or just posterior. Okay. This quantity over here of data given parameters is called the likelihood. This quantity over here is called the prior, and this is a normalization constant to ensure that this is formally a probability density. So this is called the evidence. Okay. All right. It is also sometimes referred to as the marginal likelihood, but evidence is shorter on the tongue, so I'm going to use evidence. Okay. All right. So the likelihood is essentially what the data is telling you about the source parameters. This quantity over here called the prior is something that you are sure from beforehand must be the case. That's your prior information. So for example, if supposing you have parameterized your waveform in terms of mass ratio, mass 2 divided by mass 1, where mass 2 is the smaller of the two masses, then what you can say is, I am sure that the mass ratio must lie between 0 and 1. Okay, it cannot exceed 1. So you can ensure that that is the case by putting in a prior information here. Okay. So what is this likelihood? So the likelihood is for gravitational waves proportional exponential negative data minus template, inner product data minus template divided by 2. Where I should probably be more complete. I will say that templates, of course, are dependent on the parameters. Okay. So this is your likelihood function. It is a function of the theta parameters because your templates are a function of theta parameters. And then when you put this and construct your posterior, you essentially need to sample a distribution that is 15 dimensional because H depends on all those parameters, right, that I talked about. So this is a very high dimensional distribution that you need to sample, and therefore using a simple grid method to grid over your different parameters will be virtually impossible to do with existing computers today. It's just far too much parameter space to cover in a simple grid method. There are alternatives to the grid method such as the Markov chain Monte Carlo method and various other sampling methods that exist that I'm not going to go over here. But just to let you know that there are ways by which you can sample this high dimensional posterior. And once you sample this high dimensional posterior, you can get distributions on your source parameters. Okay. So let me. Am I doing on time? Okay. Time. So this posterior, which is a joint posterior on all your parameters, mass 1, mass 2, spin 1, spin 2, luminosity distance, right ascension, declination, blah, blah, blah. All of that is contained here, given the data, right? But sometimes what you're interested in, say, is just I want to know what are the masses of my source, for example. So then what you do is you do a process called marginalization where you marginalize out what your nuisance. So say for simplicity, your theta essentially contains just mass 1 and mass 2 given data. This is not true, it contains 15 parameters. But let us say it just contains mass 1 and mass 2. then if I wanted what is P of mass 1 given the data, I would need to marginalize out with respect to the other parameter, right? Over some appropriate range. So say for black holes, I know that the masses go from say 5 to 100 for the kind of binary black holes that LIGO detects. So this will be say from 5 solar masses to 8 solar masses. Right? So then you end up with a posterior distribution on mass 1. Suppose you wanted posterior distribution on mass 1 and mass 2. Then you have to marginalize out all the other parameters. Take that many integrals and marginalize out. Okay? That would be the method. Alright. Now, so let me just write down. So this is the process of parameter estimation. You construct the posterior, marginalize out your nuisance parameters. You can think of parameter estimation, PE, as a Bayesian fitting process. Now, why do I say that? This is ultimately a fitting process, just like your least square fit. And the reason I'm saying that this is ultimately a fitting process, and that is because you had assumed a model on the waveform. You assumed that the waveform follows general relativity. So you have some model that was imposed, okay? And then you use that model and then you determine what were the free parameters of that model. Just like when you're trying to fit a straight line, you're assuming the model to be a straight line and then you determine what is the slope of the line and what is the abscissa where it intersects with the y-axis. So it's something very similar in that sense, okay? So what this goes to show is that your Bayesian inference of the parameters is model dependent. So then the next question you could ask is, how do I know I have the correct model? Right? And if I don't have the correct model, how do I get to the correct model? That's another question you might ask, right? So for example, for the purposes of this particular workshop, you might ask the question, supposing I want to determine whether beyond GR theories exist or not, okay? So I could ask, is GR correct or is some other beyond GR model correct? How do I test that? How do I test which model is true? Okay, because here so far I assumed a model and determined the parameters. So the way that you would do this is a method called Bayesian model selection, okay? And even though it sounds very heavy, it's actually extremely straightforward. So Bayesian model selection. So say you have two models for your H, for your waveform. One which is parametrized by a set of parameters θ1 under some hypothesis H1, say the hypothesis is GR, and say you have another model, a waveform θ2, which is parameterized by parameters θ2 under some beyond GR hypothesis 2. And I want to ask the question, which of these two models is preferred by the data? So the way you can do this is by evaluating what is called a Bayes factor B12, and that is simply by the following. The likelihood, a set of parameters, each one. One second. Did I do that? Yeah, that's correct. It is a ratio of marginal likelihoods. The likelihood of your parameters theta 1 under hypothesis 1 times the prior, okay, integrated. And if you remember your Bayes theorem, if the posterior has to be normalized, then what is sitting in your denominator is effectively this integral, okay. So then effectively what you have is a ratio of evidences, Z1 by Z2, okay. Now depending on this value, so if B12 is greater than 1, like significantly greater than 1 in value, then you know that hypothesis 1 is much preferred over hypothesis 2. If it is the other way around, if you did B21 and found that B is much greater than 1, then your hypothesis 2 is preferred over hypothesis 1. Now if your Bayes factor is hovering around 1, then essentially what you can say is that your data is unable to tell you which of the two models is preferred, okay. Sense? Yes.
This can be satisfied via this scenario, like so suppose we have two waveforms coming from modified gravity and GR.
Right.
And GR does not have some physics which modified gravity.
Correct.
Holds,
Yes.
such that modified gravity waveform as
Right.
SNR peak greater than GR.
No, SNR peak here doesn't matter. So this one should not. So one has to be very careful. Like I said, there can be certain waveforms that are not truly representative of the signaling data, but they are good at pulling it out. So it doesn't matter if you have a large SNR from a given template. It doesn't guarantee that your template or model is correct. It doesn't guarantee that. The only way you can really guarantee it is by formally doing this process. And even then you can only be sure if this Bayes factor is large. If this Bayes factor is around 1, then you still don't know which of the two is preferred. Okay. Any other questions?
Considering the same example,
Yes.
since the modified gravity waveform will have more parameters
Yeah.
than the GR,
Yeah.
won't it already fit?
No, not necessarily. No, not necessarily. It's not true. So what will happen in such cases is that basically what you will find is in your recovery of these extra parameters, they will all be consistent with 0 so that it converges back to GR. And when you do the ratio of evidences, you will find that it's approximately 1, which is basically telling you that the model with extra sophistication is not something that the data definitely prefers. A GR is good enough. Okay. Right. Of course, you could really go crazy, put like 100 and 1,000 or 10,000 parameters so that you completely overfit the data. But then you may get it to work for one noise realization, but it will not work for another noise realization.
But we have just one noise realization. I mean, from like I'm talking about real gravity.
No, you have given a PSD, you can have multiple noise realization, ergodic principle, right? If your PSD doesn't change as a function of time, if you wait long enough, you will get a different noise realization, right?
No, but suppose I have an event.
Yes.
I have some strain wave.
Yes.
The noise for that strain stretch is fixed.
Correct. And say you overfit there. Now you get another event and you use the same model there, it will not work. And since that beyond GR theory has to work everywhere, you can be sure that you have overfitted over there, right? Okay. Right.
Essentially, when I'm talking about, let's say,
Right.
with respect to the parameter, I would need my priors to be very accurate. Prior will play a very important role, or it would be like.
So that's a good question. So the way I would put it is that the less role your prior plays, the more information your data is having. If you find that by changing your prior, your posterior is changing wildly, you can be sure that your data has nothing in it, basically. It is not informing you anything. Everything is coming from your prior assumptions on what is inside, right? So that is why in the LIGO-Virgo-Kagra collaboration, a lot of the runs have multiple priors, and then they rerun the event, and they just check whether the recovery on the posterior is deviating as a function of change prior. Right?
Ideally, it shouldn't depend. Right?
Ideally, yes. So 150914, it didn't depend too much on the prior, right? It was such a loud event. Yeah. So, any other questions? Okay, so so now I want to ask two questions, and then I don't know, at 5:30 I'll basically stop. So let me ask two questions that are essentially the questions that I want to address in my lecture series, or two lecture series, if you can call it a series. Given a set of events, known to be gravitational waves, taken over some observation time, what is the intrinsic rate? Where rate I defined right at the beginning of this lecture. Okay? The number per unit time co-moving, the number per source frame time per co-moving volume. Okay? And the second question is same things assumed, and conducted on all the events, parameter estimation conducted. What is the mass distribution of binary black holes, or you can choose binary neutron stars have also been detected, so you can ask what is the mass distribution of binary neutron stars. Okay. Let me just start with the first one and give you a very simple derivation, and then I'll stop. So I'm going to make an assumption when I calculate the rate. Okay. So what I'm going to say is that the BBH events occur as a Poisson process. Okay. Okay. So that's the assumption I'm going to make. Now, once I have made this assumption, let us suppose that I have n confident detections. So I have n detections basically. So n BBHs, let's say. All right. Okay. So then what I can say is that my likelihood on these n events, given the Poisson mean that I do not yet know, but I do know that there are n events, okay? This must follow a Poisson distribution, okay? 1 over right? I guess everyone is familiar with what a Poisson distribution is, right? Okay. So now, what I'm interested in is the rate r, which I define as the Poisson mean divided by a population averaged space-time volume sensitivity Vt. Okay. All right. So the first step, I'll come to what I mean exactly by a population average space-time volume sensitivity. But for now, let me focus on this Poisson mean. Okay. So the posterior on the Poisson mean given n, I can acquire from the likelihood using Bayes' theorem. Yes? Divided by some normalization. Right? Does that make sense? Okay, great. So let me apply this. I don't know what I keep doing with the duster. Okay, I keep putting it there. All right. So let me take an example. Okay. In the first observing run, there were no binary neutron stars detected at all. There's only binary black holes. Okay. So in O1 for BNS, n equals 0. Okay. So then Pn given lambda, what is that going to be? I put n equals to 0 there, right? So that's going to be 1 over 0 factorial lambda to the 0, that's 1. That's just exponential minus lambda, right? Now, let me suppose that my prior on lambda is some constant between two values of lambda, okay? So, I'm going to say it is a uniform prior, okay? So, essentially then, my P lambda given n is simply some normalization times exponential minus lambda, okay? What is this normalization constant? Well, you get it by making sure that this is a density, right? So integral 0 to infinity P lambda given n d lambda must equal 1. So A integral 0 to infinity exponential minus lambda must equal 1. What is this? This is minus exponential minus lambda 0 to infinity. When you put both of these in, you will just end up getting 1. So essentially, this exponential minus lambda is already normalized. So this, I'm going to be a bit lazy with my writing and just say, this was the posterior on the Poisson mean that was derived at the end of the first observing run for binary neutron star events. Okay? But we are not there yet. What we want is the rate. So for that we need to determine the space-time volume sensitivity population averaged. Okay. Okay, I have run out of time, is it? Is Subhit here? I'll keep going until he comes, yeah. Okay, sure, yeah. Just let me know when to stop. Otherwise I'll keep going. Alright, so space-time volume sensitivity. So what is this quantity Vt? Essentially, this quantity Vt is a measure of how much space-time volume is accessible to you. So your detector cannot see everything, okay? It is better at seeing sources that are near. It is better at seeing sources that are more massive, okay? That's straightforward enough to understand, right? Sources that are light more far away are typically missed. In astronomy jargon, this is referred to as the Malmquist bias. But anyway, so we need to be able to estimate what is this space-time volume sensitivity, okay, Vt of the detector. How do we do this? Now remember, we want co-moving volume and we want source frame time. Okay, that you remember right at the beginning, that's what I said as my rate, what it's going to be. So I'll come to the population average part a bit later. For now, I'm going to say that my Vt is just this, right? Differential co-moving volume, differential source frame time. Okay. So now what I do is I do some jugglery. I'm going to say this is so what have I done here? Essentially, I've divided and multiplied by dz. So over here what I get is this so-called differential co-moving volume as a function of z. Now, in FRW cosmology, dt source divided by dt in the detector frame is just 1 over 1 plus z. Okay? So this is then okay? All right. Should I stop? Or should I finish? Okay, yeah. All right. Now, I have my Vt, which is that double integral. Okay. Now, what I've effectively done by doing this is that I have converted from source frame time to detector frame time. All right. Now, dvc by dz only depends on the redshift z, right? It doesn't depend on the detector frame time. So effectively, one integral is basically done. So what you have is t observation integral 1 over 1 plus z. Sorry, I missed a dz here. Okay. Make sense? Now, the next question is, what should I take as the integral over here? Okay, what limit should I take? So this is essentially going to be determined by how far away your detector can see, right? So it should be integrated till that. So if to do it in a better way, it will be from 0 to wherever your detector can see, z det, right? Now the way you determine this is as follows. What you say is that I'm gonna do this 0 to infinity. However, I'm going to introduce a selection function which captures what are the sources that are detectable. Okay? Any questions on this? Now it turns out that our sources are not just dependent on Z. Like I mentioned, they are also dependent on how massive they are. The more massive your source is, the further out you can see. So you need to find a way to also introduce a selection function as a function of the source parameters like masses. Okay. So what you then do is you say that this is equal to, or rather, sorry, I should not, let me just, is he, should I stop? Is he coming?
He's there. We were just waiting for some tea.
Oh, okay.
Maybe how much more?
Oh, it is another tea session, is it?
No tea session.
Okay.
Because the next lecture happens to be start at 5:30.
Huh.
Which has no place for me. So we thought that we'll have 10 minutes break and then start.
Oh, am I killing people's tea time? I can stop.
No, I mean, so how much more will VC get? VT?
It'll take probably 2 more minutes.
Okay, then we can stop then and then the tea.
Okay, fine. And if people are still confused about this VT business, I can take that up tomorrow. I don't need to take questions now. Okay? So, my population averaged space-time volume sensitivity is T observation so this is theta not including z. Okay. Oh, I'm sorry. No, this is including z. Comma z. Right. Okay. There. Okay. So what exactly is this selection function? The selection function can be thought of as a fraction. This is the fraction of events that cross the detection threshold with parameters theta and redshift z. Okay. So the way this selection function is evaluated is that it is done numerically. You essentially inject in your data sources at different redshift, and at each redshift you inject a distribution of masses, and then you calculate what is the fraction of those events that cross the threshold, and that essentially is your f. So you can repeat this for different redshifts and you can repeat this for different masses. Does that make sense? So this is your selection function. Yes, it is. It is. Yes, yes, but they do like heavily parallelize, etc., and they find a way to do it. Yeah, but it is one of the most computationally expensive things to do. Yeah, absolutely. Yeah, it requires a lot of these injection calculators. You have to do it across multiple redshifts. But of course, you can get a bit clever, and then you can say that a certain redshift, I know it's not going to be detectable, so you can just start to reject beyond a certain redshift. You can just say that a fraction of 0 will be detectable beyond a redshift of 5, for example. You're sure. So then you don't need to go all the way to redshift of 100, right? So forth. Yeah.
And also that is motivated from astrophysical models like.
Yes. So your VT is dependent on your population. That's why it's called population averaged. So you need to, so obviously depending on how the masses are distributed, your space-time volume sensitivity will change, right? If supposing your masses are skewed toward heavier masses, your space-time volume sensitivity will be larger because this fraction will be larger. If it's skewed toward lower masses, it will be smaller, right? So yes. Done. This is my space-time volume sensitivity. And then you can convert your posterior on the count to a posterior on the rate. That I will just tell you tomorrow.